Now it's possible for an alternating series to converge with the alternating part included, but then diverge when you take out the alternating part. So we have what's known as conditional convergence, which is the latter. So if you have the alternating series converging but the non-alternating counterpart diverging, versus absolute convergence where both of them converge. So let's take a look at some examples with that and determine how to identify this. So determine whether the series converges absolutely, conditionally, or diverges. Okay, so I have the sum from n equals 1 to infinity of -1 to the n plus 1 over 3n plus 1. So to see if the alternating series converges, we can just start with the alternating series test, and that would begin taking the limit as n goes to infinity of the non-alternating terms. And since this is the limit of a polynomial, we of course, or a limit of a rational, we could of course use L'Hopital's rule, or we can just say the degree of the denominator is larger, so this limit goes to 0. That's fine. All right, so that checks out. We also need this to be a decreasing sequence. So we check for decreasing here. So this would be 1 over 3 times n plus 1 plus 1 should be less than or equal to 1 over 3n plus 1. All right, if I cross multiply here, then 3n plus 1 should be less than or equal to, I'll go ahead and work this algebraically out. So this would be 3n plus 4, it looks like, because the 3 would distribute, and then 3 plus 1 gives me that 4. And if I subtract 3n from both sides, that's going to cancel out that term, leaving me with just 1 is less than or equal to 4, which is definitely a true statement. So it converges by the alternating series test. Then let's check the non-alternating counterpart. Which in this case would be just the series n equals 1 to infinity of 1 over 3n plus 1. And that particular test, or that particular series being a rational function, I would probably use the limit comparison test for that. So we would compare to, say, the sum n equals 1 to infinity of 1 over n, because it looks very similar to that. And that, of course, is the harmonic series. And we know that that diverges. All right, so the test here would require us to take the limit as n goes to infinity of each of these two divided. So that's the limit as n goes to infinity of n over 3n plus 1, and just using rules of infinite limits with rational functions, that's going to go to 1/3. So that is a real value, all right? It's not 0 or infinity. So that tells me that I have a result here, and therefore these two particular series are doing the same thing. So this series diverges by the limit comparison test. So the non-alternating diverges, but the alternating converges, so this is conditionally convergent. And if you work these problems out, and like for instance, if the alternating series diverges, you're guaranteed that the non-alternating series is going to also diverge. So if the alternating series diverges, then you don't have to go any further. You can just state that. If you test for absolute convergence first, well then, if the non-alternating series converges, the alternating series is definitely going to converge as well. So depends on your instructor. You might be required to go ahead and prove the alternating series converges as well. But some instructors might just say, as long as you prove absolute convergence, that implies both. So just find out from your instructor what you need to do there. All right, one more here. Determine whether this series converges absolutely, conditionally, or diverges. So this is -1 to the n over the natural log of n plus 1. So let's start with the alternating series test. First thing we need to do is take the limit as n goes to infinity of 1 over the natural log of n plus 1. Okay, so to prove this, I don't have the ability to use L'Hopital's rule, although it's tempting. But the problem is the numerator is not changing, so it's not running off to infinity. The denominator is, but not the numerator. However, I can use the fact that if the denominator is changing, and it's growing slowly, but it is growing, that because it's in the denominator, the value of the fraction is going to be pulled to 0. If you aren't convinced by an argument like that, then just grab a table and you can, convince yourself that way. But it's going to 0, so that's great, that's a result. Now we just need this to be decreasing in value. So we would have 1 over the natural log of n plus 1 plus 1. It needs to be less than or equal to 1 over the natural log of n plus 1. So multiply both sides here, and I'm going to go ahead and simplify this, the natural log of n plus 2. And if I take each side of this inequality and make it an exponent with e as its base, then e and natural log effectively kind of cancel out, leaving me just the argument. So n plus 1 less than or equal to n plus 2, and then if I subtract n from both sides, I get a very clear result here. 1 is definitely less than 2. All right, so this converges by the alternating series test, so it's at least conditionally convergent. But then let's check the non-alternating counterpart here, which is the series n equals 1 to infinity of 1 over the natural log of n plus 1. Okay, in this case, whenever you have series involving natural log, it's often kind of tricky to decide exactly what type of series to use, or series test that is to use. But I generally will go with a direct comparison test, at least first, and see if that works or not. So the direct comparison test, if we try that, we have to pick something to compare to. So we have a choice, and we can try and compare to something that converges or something that diverges. My inclination here is that this is probably diverging because the natural log grows slower than a linear function, and 1 over n does not go to 0 fast enough to converge. So I bet that this thing actually diverges. So let's just start comparing to the harmonic series, because we know that diverges. All right, now in the direct comparison test, what we need, we have the known sequence and that is diverging. So then if that's diverging, we need a series that's going to zero even slower. So we need this to be our unknown series. Okay, so I would need all the terms in the unknown to be greater than or equal to all the terms in the known sequence. And let's see what happens here. If we cross multiply, n should be greater than or equal to the natural log of n plus 1, which is true, but it's not the cleanest result here. It's not like 1 is less than 2, you know. Let's try raising both sides as a, exponential with base e. So I would have e to the n is greater than or equal to n plus 1. And that's not really a whole lot different, but I think that maybe it's at least a little bit more clear. An exponential function definitely grows a lot faster than a linear function, so I think that's clear enough to say that that works. All right, so since that works, that means that the non-alternating series and 1 over n do the same thing, so it diverges. And since the non-alternating series diverges, but the alternating series converges, that tells me that this series is also conditionally convergent.